Hello, my name is Emily Paulino, and I am here with my teammates Oscar Alvarez, Ronaldo Carrasco, Eileen Paula, and Najeline Balan Rodriguez. And we are going to be presenting our real-time driver drowsiness detection system for enhanced road safety. Our current problem is that driver drowsiness is a significant contributor to road accidents worldwide, resulting in loss of life and property. Results show that an estimated 17.6% of all fatal crashes in years 2017 to 2021 involved a drowsy driver. Over the 5-year study period, an estimated 29,834 people were killed in crashes that involved drowsy drivers. Designing and implementing a system that detects driver drowsiness in real time. We developed a non-intrusive approach using image processing and psychological data, integrating the system into a mobile app that can alert the driver effectively to mitigate potential road hazards. Currently, there are systems that detect drowsiness using steering wheel sensors, require additional devices, or are simply not available to use on the go. Our app aims to make drowsiness detection more accessible and reliable. Currently, our system is designed with a client-server architecture, where on the client side, we have our users with Expo and React Native. And on the server side, we have a backend using Flask, a drowsy model using TensorFlow, and all of those are connected to a data store, which we are using Firebase.
So to start off, our project has an authentication system, a fully functional authentication system using Firebase, which is built into a React Native mobile app via Expo. The user can sign up by entering their name, email, password, phone number, and emergency contact information. We have a function called Create User that handles both authentication through Firebase Auth and also stores additional user data in Firestore under their unique user ID. This ensures that the secure account is created while also capturing critical emergency info for the app's use case.
For returning users, the login page allows secure access by validating credentials through Firebase with a login user function. Upon successful login, users are authenticated and redirected to the main app to experience. To maintain user privacy and session control, the logout user function allows users to securely sign out at any time.
As the authentication process develops, it handles errors gracefully with both the login and sign up processes. This is also using Firebase. Certain errors like an invalid email address or the length of the characters within a password deliver user-friendly messages within the UI. And this is important so that the storage is done effectively, specifically with the phone number and emergency contact info, which is stored in Firestore as opposed to Firebase Auth, which allows for flexibility and structured user profiles, especially when it comes to the use of this information in regards to the drowsiness of the driver.
Moving on to the home and profile page, users can submit structured data through the app's interface, which is then stored in Firestore using a save data function. Each entry is organized under the authenticated user's unique ID, allowing for personalized and secure data storage. This ensures that all information is tied directly to the individual user account. To access previously stored data, a fetch data function queries Firestore and retrieves relevant documents based on the user's ID. The data is then displayed in real time within the app, giving users a seamless and dynamic experience. Moving along to the stats page, this file displays the user's alertness data over time. It shows a line graph that tracks 3 states: alert, low vigilant, and very drowsy, using different colored lines. Below the graph, it presents a list of recording video sessions, each with alertness stats like eyes closed, yawning, and alertness percentages. The data is pulled from Firebase for the currently logged in user and then updates in real time when a new video data is stored.
For the camera page, it will automatically begin waiting, and once that wait duration is over, it will begin to record. This video will then be sent to the backend. The backend will then see that there's a video and automatically process that video. The video will then send the output to the front end, which will be displayed in the top right corner. And you can view the wait durations and all that information at the top with a progress bar. If the user is drowsy, it will play an audio. And for the settings page, there are a couple of settings: the help page, which describes how to use the app, a camera access, which will route the user to the settings, which will allow them to turn off or on the camera, a driver safety link, which will send that user to a website that explains everything, all the dangers of driving drowsy. And a report page will send the user to the GitHub so they can report a problem. For the backend and the database, they're very close put together. The backend is written in Flask, and the database, as said before, is written in Firebase. The user, when they create their account, it automatically inputs all the variables and attributes into the user. And whenever a video is received, it will automatically be placed in a fire storage, which the user has a path to it, a collection. And once the model processes the video, it will automatically update the video attribute with all the values. And if the user is drowsy, it will automatically send a SMS to the emergency contact.
System takes spatial video frames as input and simultaneously performs 3 predictions: the level of drowsiness, whether the person is yawning, and if their eyes are open or closed. It uses a single MobileNet V2 model with 3 output heads, one for each task. This diagram illustrates the full pipeline. It begins with facial preprocessing and feature extraction, including contrast enhancement and MAR-based yawning filtering. Then the data is split and fed into a unified model, which is evaluated using test sets for each task. We use 4 datasets. RLDD and DDD provide labeled frames for drowsiness. GoDDD helps classifying yawning, and Unity Eyes enables blinking detection using eye state labels. Due to the size, these datasets are referenced but not included in the GitHub repo. The model shares one feature extractor, MobileNet V2, and uses 3 independent heads. Each head is trained on a different classification task with categorical cross-entropy loss. The training uses real-time augmentation with TensorFlow's image data generator. Here's a breakdown of key evaluation metrics for the drowsiness classification head. It achieved nearly perfect accuracy and ROC-AUC, indicating excellent performance. These metrics include precision, recall, and N1 score calculated per class. And then these confusion matrices help visualize how well the model predicted each class. Drowsiness predictions were nearly flawless. Yawning, however, proved more difficult due to class imbalance and subtle expression differences. Linking performance was moderate.
The way that we implemented the model into our application was after the Export app records a video and uploads it to Firebase, Firestore tracks analysis results, and we have a Python script waiting for any pending videos in Firestore. Python then pulls the videos, analyzes them, and writes results back to Firebase. The app is then updated with drowsiness alerts based on backend response, and the analysis results are stored for the statistics page. And these are our references.